Good evening, everyone. Welcome to this problem session. So I was saying, in this case, like for this particular session, we are going to identify Maxwell's amplifier circuit, and then we will solve the fact. But rather than going for internal circuitry of op-amp, we will see the external properties of op-amp, and we will solve the problem based on external properties. By this time, we will be using the black box concentration for the op-amp and solve the problem. Okay? So with this information, we will so the first problem that we have today is this configuration, and you all know by now that this is a series amplifier. So in this particular series amplifier, all the parameters are given for the two transistors, with the capacitors, all the load capacitors and connecting capacitors, and here we have to find the DC gate voltage per input. So for this transistor input, what is the gate voltage that is appearing in the this transistor gate input? So it is given that R1 is 90K, R2 is 30K, R3 is 60K, C1, C2 are 10 microfarad, CL is 100 picofarad, C3 is very high, so here it is C3, very high. So let's say it's very high, so maybe I will say 1 millifarad for now, but its value is not mentioned yet. Somebody wants to say something?
My voice is still not clear for me. I am not sure for other people.
Ma'am, same ma'am. Could you please unmute rest of them, ma'am? Because some external noise also is getting added. Totally, it is getting amplified.
Okay, yeah. So now is it okay? Only one person unmute and answer. Is it okay now?
Yes, ma'am. Yes, ma'am. Continue, ma'am. Means, could you speak little bit higher, ma'am? Because you are using this headset now. If whenever you are using this headset, you need to speak little bit louder than the previous.
Speak a little louder.
Yes, ma'am.
Okay, but that noise problem is not there, right?
Yeah, ma'am. If you speak louder, it won't be there. Means
Oh.
I'm also using the same headsets. That's why.
Oh, okay. So yeah, I was saying these are the parameters given. Other than that, we know that CGS is like 10 picofarad, CGD is 5 picofarad, VD is 12 volts, lambda 1, lambda 2 are given, VTS is Kn and Kp are given, like Knw by L, Kpw by L. Now, what I am saying is, so let's say here it says that you have to find the DC gate voltage for transistor N2. For transistor N2, to find the DC gate voltage, we need to know this point voltage, right? To know this node voltage, we need to know this node voltage, so that we can simply apply the voltage division rule and get the values for this particular gate voltage VG2. But unfortunately, R4 is not given. So now what we'll do, let's observe this transistor M1. So in this transistor M1, here what is the gate voltage for transistor M1, which will be VGS1. Then applying that same voltage division rule, we will get 30 by. So VGS1 is 3 volts. Right? Now, one thing is very clear that the current which is flowing through transistor M1 is the same current that is flowing through transistor M2. Since it is a DC current, this capacitor will not see any current, so it will not pass through these capacitors. So the only current that is flowing through both the transistors M1 and M2 will be equal. So using that same concept, you can see that M2 is a PMOS transistor and M1 is an NMOS transistor. Since it is an amplifier configuration, we'll go for saturation expression, right? Like
Ma'am,
the
ma'am, I have
transistor.
small doubt.
Sorry, yes.
Yeah, ma'am. In this case, okay, when in cascode current is buffer means M1 to M1 current will be same, right? What you said, ma'am. Yeah, but in the given case that when you are performing a DC analysis, C3 will be open circuit, right? And R3 and R4 will also generate some current, right?
Okay, so you are saying that so it is like in this branch when we are going for R3 and R4.
Yes, ma'am. It will also generate some current. Na? Whenever if you go for KCL, the current across the M2 is drawing some current, and current through R4 will get some current. The resultant across the drain will be summation of two currents, right?
Right, I agree. But one thing that R4 is not known, and secondly, whenever there is a bias uh, circuit, right? When you are biasing your transistor using resistors or any other circuitry, it is made sure that it does not draw more than like 10% of your current. It is very low. Like it is made such that your bias circuit draws very less current. So it is almost equivalent to like you can simply neglect it compared to your main current, which is the current flowing through your transistor. You can neglect that. Yeah, I understand that you can consider that current if let's say R4 was also given. So you could also consider that current which is flowing from VDD to this. You can consider that, but it will be very small in proportion. So we can simply, like it is safe to neglect that particular current. So we can say that now the currents through the transistors are equal, considering that they are in series combination. As if these two transistors are like these two resistors, R3 and R4, are not drawing very high current. Because you can already see like R3 is 60 kilo, R3 is 60 kilo, and R4 will also be in few kilo. So the current that will be there through these two resistors will be very low. So we can neglect that.
Okay, get the point. Thank you, ma'am.
Yeah. So maybe I'll write also. So just in case if somebody um, wants to refer. So assume that R3 and R4 drawn negligible current. Considering R3 and R4 draw negligible current, we'll say that ID1 is equal to ID2. Now your ID1 is for N-type transistor, ID2 is for P-type transistor. So this is the first assumption. Second is N1 and N2 in saturation. Yeah. So with this assumption, we'll write equation is whole square, K3 W by 2 VHG minus mod VTH of whole square. Now here, so substituting the value 7.5 VGS 3 volts minus 1 whole square is equal to Kp, that is 2 milliamperes per volt square by 2. VSC, so that is 12 minus VG2 minus 1 whole square. Kp cancel. Because 11 minus Vg equal to plus minus 1. So now 12 plus 1. Vg is equal to 11 minus 1, that is 10 volts. So minus 1. Vg, that is 12 volts. But can Vg be 12 volts? That is the question. So in this particular diagram, if you look at it very carefully, there is already a resistor of 60K, another resistor R4. So definitely your Vg2 cannot be equal to Vg or Vgd, right? So Vg2 cannot be equal to 12 volts. So that's why we'll discard this and we'll say that our Vg2 for transistor N2 is 10 volts. And VGS for the VSG for the same transistor is 12 minus 10, that is 2 volts. This is clear, right? Very simple analysis. Huh? Are there any doubts?
Ma'am, I could not understand, like, I was not able to hear properly this 12 volt. Is it like that saturation condition only we are verifying?
There,
Or this VG equal to 11 plus 1 equal to 12 volt, we are not considering. So, saturation.
so this condition is fine. Secondly, you can observe that see, VG2 is this particular point, right? This point is your VG2. Now this point is connected to a resistor divider, right?
Yeah.
This point is higher than your ground. So the net voltage across this resistor divider is already less than 12 volts. So how can you get the gate voltage of 12 over here? That is not possible, right?
Okay, okay, okay. Mm-hmm.
So we will simply discuss this.
Okay. Yeah, yeah.
We know that okay, since gate voltage cannot be 12 volts, so then the voltage that is actually appearing at the gate is 10 volts.
Okay, okay.
Now, after this, let's move on to the next part for the same session. So in this session again, it says that we have to find the value of resistor R4.
Ma'am, before going to this, could you please, before that, you said, no, ma'am, that KCL equation, you can ignore that current across R4. Could you please show it in mathematical form, ma'am? How can we ignore it?
So here, since R4 is not there,
Mm.
but generally what we consider while designing also, it gets us around 10% of current. And here also in next problem here we are solving for R4, right? So
Yes,
let's say calculating this R4, what is the current that we are actually getting across that particular branch? So we can get it right from there.
okay, ma'am. Continue.
Yeah. So in this particular question, we have to find the resistor R4 such that the same current flows through the transistor N1 and N2, which is shown in this particular figure. So we know the current equation is W A3L VGS minus VGH whole square 1 plus lambda VDS, right, for NMOS. And similarly, we can write it for CMOS. And here we are considering lambda because lambda was mentioned in the property. Now, the next question that might appear is, okay, when we are considering lambda over here, why are we not considering lambda in the previous question? Right? It's a very genuine doubt. Here, I didn't consider the lambda equation. I went to using the simple equation, right? So, why we didn't consider lambda is because at this node, the voltage that we need to find out, that is VD node, is not clear. And unfortunately, how do we find VD voltage? We generally find it through the KVL, right? But here, if we write KVL, so it will appear as 12 equal to VSD2 minus VDS1, which ultimately becomes 12 minus, 12 equal to 12 minus VD minus VD. So these two actually cancel. So unfortunately, we are unable to solve it. So that's why we are moving ahead with like this safer, like smaller expression. And also we know that lambda is very small, which is 0.01 and 0.015 times of VD. And VD will also be definitely small. So that's why we have neglected for the calculation simplicity. But here, since now we are calculating like current, so we can go for the exact current. And we'll solve for the exact current and see what is the value that we are getting. Okay. So here we'll write ID1 equal to ID2 because gate voltage was important over there. Now here already we know the gate voltage. So the gate voltage that we have solved in problem 1, we'll use that here. And using that, we'll solve for output voltage and then we will solve for the resistor R4. So that is how we are going to proceed. So here it is. Given that we write here. VGS minus VGS whole square 1 plus lambda VGS equal to KP divided by VSD minus not VGS square 1 plus lambda VSD. Okay. It's given that there is 0.5 by 2 VGS minus KP whole square 1 plus lambda lambda 1 to consider. Okay, V0, let's say this is V0 equal to 2 by 2 into VSD equal minus 10 minus 1 square 1 plus 0.015 0.015 into VSD. So it is 12 minus V0. And now solving that 0.5 into 4 1 plus 0.01 V0 is equal to 2 into 1. Yes. Yes. Any doubt?
One 1.8 man, 0.18. 0.015 into 12, it would be 0.18.
0.18?
Yes, ma'am.
Okay, 0.18 minus 0.015 V0. So from here, the value of V0 that we get is 7.3 volts. Okay. So now, here we have got that, okay, the value of V0 is 7.2 volts. So here we have 7.2 volts. We know that a current is flowing, okay? The current is let's say IA. So the current which is flowing through R3, the same current will flow through R4 also, right? And we know that at this point the voltage is 10 volts, here it is 12 volts, and here it is 10.2 volts. So let's write simple KCL at this 10 volts node, okay? So 10 minus 12 by 60k, right? So 60k is 10 minus 7.2 by R4 is equal to 0.
4 kilo ohms, ma'am. 84.
4. So R4 that we are getting is 84 kilo ohms. Now, as I mentioned earlier also, now let's see how much is the current that is actually flowing through that path. So it is 60k already for R3. R4 is 84k. So total R is how much? 60 plus 84. 144 kilo ohms is R. And what is the potential difference between these 2 points? That is 12 minus 7.2, 4.8. So V is 4.8 volts. So the current that we are actually getting is how much?
0.03 milliamperes, ma'am. If you consider in microamperes, 33 microamperes, ma'am.
33 microamperes, right?
Yes.
And how much is the current that we are getting for, like, let's say any one current that we are getting? How much is the current we are getting for these? Let's see from the simple calculation only, it is also will get the value. It is 0.5 into, right? So 1 milliamperes around, right? So the current through the transistors is around 1 milliamperes, whereas it is around 33 microamperes. And if you consider like the exact value of current for 1 plus lambda radius one, so it will definitely increase by some amount, right? The current will definitely increase. So it is always much higher compared to your biasing like branch. So you could safely ignore it. But if you have all the like necessary information which is required to solve, you can always solve it. That's not a problem. But since there were many unknowns at that particular point, so that's why it was safe to like assume that very negligible amount of current is flowing. Clear?
Ma'am, a small question, ma'am. Here we get 1 milliampere current in through a MOSFET 2 through resistor 33 microamperes. We cannot neglect now. It is not much greater than, right?
So I'm saying 1 milliampere when did you get 1 milliampere? When you just consider the exact current, 1 plus lambda VDS one, right? Now if you consider like 1 plus lambda VDS wala current, so how much will you get?
Okay.
Consider this amount also. To increase, right? And generally it is around 10%. Like biasing branch will carry around 10% of their current. So it's around like 1.1 milliamperes. And the current that you are getting through your bias
Yes, ma'am.
3 amperes. That is very small, like you can neglect it. But yeah, if you are like willing to solve it that way also, it will not change the results much. But for that, there were a lot of things that need to solve. First of all, you need to know your output voltage, the node voltage, second, the resistor value. All these need to be, like, when we are able to solve such current, then all of these things are known, right? The potential at this output node and the resistor value, then only you can completely solve the current. At that particular point, how would you have solved the current when you don't even know the gate voltage for one transistor? Then output voltages are not known, and also the resistor value is unknown. So it's very tedious job, right? And we know that it cannot go beyond 10%. It will always be less than 10% majority of the time. So it is safe to like ignore that value. So that's why we assume that okay, negligible amount of current is flowing and we eliminated the same. Is it clear?
Yes, ma'am.
Now let's move on to the next problem. So yeah, in this problem, again for the same circuit, it is asked that you have to find the gain, that is V naught by Vn, and the mid-frequency range of the amplifier circuit. So what do you understand by the mid-frequency range? When they say, okay, like mid-frequency range, let us know the gain. What do they want you to know? Like what is the main concern in this particular question? What does mid-frequency range mean?
Ma'am, means if you don't maintain the means frequency in a proper manner, then if during DC analysis, capacitor won't be an open circuit, uh, and during AC analysis, capacitor C1 won't be in a short circuit. So, in order to this, we need to know about frequency range accurately. I'm with my knowledge, ma'am.
Okay. So to make things very simple, I'll let you know. See, we all know that these the gain profile is frequency dependent because when we go for AC, we know that capacitors will come into picture, and these capacitors, since they are frequency dependent components, so they will change your profile or um, your response of your amplifier based on frequency. This is clear to everyone, right? So, ideally, what happens due to the presence of these capacitors, you get somewhat this type of curve for your gain versus frequency plot. Okay. Due to intrinsic capacitors or load capacitors that you use, you get this type of profile. Now, in this thing, you can see that for very low frequencies also you observe that your gain is dropping, and for very high frequency also, your gain starts to reduce. There is a certain range of frequency for which your gain actually stays constant and remains constant, and that frequency range is what is known as mid-frequency range. From this frequency profile also, you can observe that it is somewhere in the between, right? Like it is not like it's not a low frequency profile or not in high frequency, rather it's somewhere in between where your gain stays constant. And what you ideally want is, let's say you are designing an amplifier with a gain of like 80 dB. So you want your amplifier to provide you a gain of 80 dB, right? Say for one frequency, it is providing you a gain of 40 dB, other it is providing you the gain of 80 dB. So you want for your operational frequency range, your amplifier should provide you the same gain that you design it for. So that is the idea. Okay. So when they say like mid-frequency range, ideally they mean the gain for so the constant and maximum gain that you can achieve from your system or your circuit. So that is what they mean by mid-frequency range. Sometimes it is also known as DC gain, like DC gain. That is because for some circuits the profile is like this for frequency versus gain. So like for very low frequencies, it does not roll off. Your gain does not reduce. and it stays at the maximum. Then at higher frequencies, it starts to reduce. So for those type of circuits, it is called as DC gain. And when the profile is like this, for this type of circuit, that is known as mid-frequency range. So ultimately, what they want you to calculate is the gain, which is like the maximum gain that you can get from your circuit. And also, this is the only gain which will stay for a, like, which will stay constant for a certain range of frequencies. So this is actually the gain that you are getting out of your circuit. Is it clear? Any doubts in
Yes,
that?
ma'am. Yes, ma'am. Clear, ma'am.
After knowing this, so we know they are asking gain, right? And it's a CS amplifier. So when it is a CS amplifier, how do we write gain? What is the simplest way of writing gain?
Minus GM into RL, ma'am. GM into R out, sorry.
Gain into, let's write it as zero. Okay? Minus gain into zero. So how do we calculate gain? There are two transistors, right?
Yes, ma'am. If we apply test voltage.
So which transistor will get C? GM into Z out. Right? So you have to calculate GM.
M1, ma'am.
M1.
Yes. So GM
Ma'am,
will
why my reason is why M1 is because if you see the voltage drop in DC analysis, there would be a voltage drop across R2, and AC analysis there is a voltage if you see a differential amplifier, whenever input is applied to that particular transistor, in most of the cases, the transconductance would be across across that MOSFET itself.
So I tell you, it's like in a very simple manner, just a single statement. Then you are saying, okay, gain equal to GM into Z out, right? So the GM term always comes from the transistor where you provide input. The transistor which takes input, it generally provides you the GM, and then Z out you will calculate at the output node. The very simple thing that you can keep in mind, that for GM you will always use the input transistor, the transistor where you provide input to, and for Z out you will simply calculate the resistance at the output node. Is it clear?
Yes, ma'am. Yes, ma'am.
Yeah, it's very simple. So first thing that we have to find out is, okay, which transistor is actually getting my input. For that particular transistor, we'll calculate the GM, and Z out will calculate accordingly. So here it will be GM1. M1 transistor is receiving the input, so it will be GM1. And the formula for GM is VGS divided by L, VGS minus VGS, correct? Now, this value is already given to us as GMW by L, right? GM1 was 0.5 milliamperes per volt square. Increase was 3 minus 1. So GM1 is 1 millisiemen. Now we have to find, okay, what is the Z out? So what are the resistors that we see at the output node? So
Ma'am, R01 and R02, ma'am. And there is one more resistor, R4.
yes, this R4 is also there, right?
Yes,
So
ma'am.
Z out we can write it as R01 parallel R02 parallel R4. So R01, how do we write? R01 is
Ma'am, what about one more resistor, ma'am? There is one more resistor in series with R4, right? R3.
R3, no?
R3 is also means parallel with VDD, right? Means R3 is connected to the ground and connected to the gate.
So from there it will see, okay, so this is a node. If I don't put this node to like AC ground, then I can consider it like, okay, R3 plus R4. So you can write it like R3 plus R4 considering that this will be actually AC ground, this is already AC ground. So I'm not considering this particular node as AC ground separately. For this transistor, this gate node, I'm not considering it as AC ground separately. So yeah, so it will be like R3 plus R4. So 1 by VD1, so this is 1 by lambda ID1. So ID we already calculated, I guess, right?
1
So
milliampere.
this
One
particular thing where AC ground is considered, so that will be short circuit. So, like, suppose this C3 is.
There is another C3 also. It was mentioned that C3 is very high.
Mm-hmm.
Capacitor is very high. It was mentioned from this. Yes, yes.
Okay, okay.
Here C3 is very high already, so we don't have to take care of this R3 as C3 is already very high. And
Mm-hmm.
so this will actually become short circuit because it will like 1 by C omega. Your C is
Mm-hmm.
high, which makes your C very small.
Mm-hmm.
So we can consider short circuit. So like we don't have to consider odds.
Yeah, yeah. So it will be like short circuited. Yeah.
Yeah, it is already short circuit
Mm.
because
Okay. Yeah,
yeah.
yeah.
So you don't have to consider so it's only the R4.
Okay. Okay.
Yeah. So this capacitor is present. Generally, this capacitor is not shown, but here it is specially mentioned, and also it is said that the charge, sorry, CP is very large. So when a capacitor is very large, its XP is already very small. So it is like make your it will make it a short circuit. So you don't have to consider R3. So you can directly write like R01, R02, and R4. So ID was 1 milliampere. So R0 will be 1 by 0.01 ampere. Similarly, R02 will be 1 by 0.0, and that is again 1 by lambda ID, 1 upon 0.015 into 1 milliampere. And this RD is R4 is 54 kilo ohm. So when we solve this parallel combination, we find out that R out is 27 volts by volt.
R01 100 kilo ohms, ma'am. R02 is 66.67 kilo ohms.
So now like this is right. Now gain is gain into 0. So minus 1 in volt. 27. So that is minus 27 volt by volt. So the gain for this circuit is minus 27 volt by volt. Correct? And why because it is a CS amplifier. Correct? Okay. So now, okay, again for the same circuit, we have to find what is the input capacitance of the amplifier circuit. Where is the input? So this node is input. So the input capacitance. So uh, capacitors are coming into picture, so that means an AC analysis. So what we'll do, we'll simply short circuit this C1. We'll say that C1 is already short circuited. Now, at this particular node, you have to say, okay, how many capacitors that you can fit. So what are the capacitors that will come into picture? So there are no external capacitors which are connected to this particular node, right? So there will only be a parasitic capacitor which will come into picture. So this is your CGA, CGD. So the capacitors that you will see at Vin will be a function of CPS and CGD. Only two capacitors. Any other capacitor which will come into picture? Because am I leaving any capacitor behind?
No, ma'am.
And then you can also observe that CT so Cn dash, because of CGD, how it will come, like how will your CGD look like?
CGD is a floating capacitance. We need to write Miller's theorem stress on that way.
Similar analysis, 1 plus A into CGD will give us this, right? Correct?
Yes, ma'am. Yes, ma'am. Correct.
1 plus A into CGD, right? So this is 1, here it goes minus
28. Ma'am, 1 plus, not 1 minus, I think.
1 minus.
1 minus, I think. 1 minus V naught by Vn by CGD.
They were considered to
Means gain should be added, I think.
say, yeah. So it is like 1 minus A, right? 1 minus A. So I already considered the sign something like that. So यहाँ पे when it is minus 27 into CGD, so it will become 28 into CGD. And again we have CGS. So it is like CGM is CGS parallel dash, which is CGS plus CM dash. So this is CGS is how much? 10 pico and 5 pico. 10 picofarad plus 28 into 5 picofarad. Yeah, this is what we are getting.
150, ma'am. 150.
CVM is 150 picofarad. Correct? So yeah, so here it is like 1 minus A or 1 plus A. So it just depends on the, okay, if you are considering the sign already while calculating your Miller analysis, then you don't have to reconsider the sign again. Okay? So yeah, it is 150 picofarad. So ye plus minus, no, it solely depends upon you, like whether you want to consider this negative of gain with another negative making it a positive, or you directly write it as positive and use the gain as mod. So it depends on you, how you consider it. So okay, we picofarad. Now let's move on to this particular question. So here you see this is an op-amp, right? So what are the basic features of an op-amp, like that you need to keep in mind? All of you, first of all, no input current. Okay, no input current, but output current is always present. There will be an output current. Its direction can be like inward or outward. That solely depends on how the circuit has been designed. But your input current is always zero. You have to keep this in mind. That is the first point. Secondly, it is considered that, okay, let's say your op-amp has very high gain. So to get that very high gain, there is a concept of virtual short. Okay, virtual short concept. So what we say that for very high gain amps, your V minus V plus. So while using, let's say, an ideal op-amp or an op-amp with very high gain, we consider that the voltages at these two nodes are equal. And considering that, we solve the equation. So now here it is grounded, right? So that means 0 volts. So here in this node also the voltage is 0 volts. But mind you that this is not an actual ground. Okay, so current will definitely flow through this branch. Current will be there, but the voltage at this node is considered very close to 0. So we consider, for solving the problem, we consider it as 0 volt. Clear? So these are the few things that you need to keep in mind while solving your op-amp based problem. Another, like, based on the configurations of your op-amp. So we have configuration. Inverting configuration means you are providing your input to the inverting node. So in this case, this is, and when we say non-inverting configuration, in non-inverting configuration, we mean input is being provided to the non-inverting terminal. RS, R, not. So in this is non-inverting, and this is inverting configuration. So for non-inverting configuration, how do you write your gain? V out by Vn. We write it as 1 plus Rs upon R. So you can simply solve it using KCL KVL. You will get this formula. And you can also remember this. These are not very difficult. Similarly, for inverting configuration, the gain you get is minus Rs upon R. Okay. So this is for inverting configuration and this is for non-inverting configuration. Now with this information, okay, so you have this amplifier and we are only talking about negative feedback over here. Okay. So output is being connected to the input at the inverting terminal or negative terminal. So this is negative feedback. Now looking at the circuit, what type of configuration is this, inverting or non-inverting?
Inverting.
Okay, right? So we know that this configuration is inverting configuration. If I write it like, okay, Z1 and Z2, so can I write V out by Vn as minus Z2 by Z1? I can write it like this, right? Then Z2 is R2 parallel C2 and Z1 is R1 parallel C1. Correct? And what do you understand by transfer function? Transfer function is basically V out by Vn, as we found out.
Yes, ma'am.
For any circuit, when we write V out by Vn, we call it as a transfer function. And what are poles and zeros? So you can write it in like H of X terms or J omega term, anything is fine. It is V out by Vn, and it will have some numerator and some denominator. Now there are the concepts of poles and zeros. So values of X, I'm only talking, since I'm talking in terms of X, so I'm writing it as in terms of X, for which numerator is equal to 0 will be 0. Okay. Now similarly, value S for the denominator is 0 will give you poles. Okay. Poles and zeros are clear. Poles and zeros are clear, right? Any doubts in poles and zero concept? No doubts, no? Okay. Considering there are no doubts. So what is the problem? So the question is, what is the location of in the given transaction? It is actually negative process. So we know that V out by Vn is minus Z2 by Z1. So it is again the follow-up question. So I'm solving it over here. So it should is Z2 by Z1 minus Z2 by Z1. Z2 has 2 into 1 of n Z2 by R2 plus 1 this is like R2 into 1 plus S R2 C2. Similarly, this one will be R1 upon 1 plus S R1 C1. H of S is equal to minus R2 1 plus S R2 C2 by R1 upon 1 plus S R1 C1. And also R2 by R1 1 plus S R1 C1 by 1 plus S R2 C2. So 0. What will be the value of 0 and what will be the value of pole? Yes, come on. What will be the value of 0 over here and what will be the value of pole over here?
Numerator will be the 0, ma'am. Denominator will be the pole.
So what is the numerator?
1 plus SRC1.
1 upon R1 C1.
Yes, ma'am.
1 plus S R1 C1 should be equal to 0. So let's say 1 plus minus 1 upon R1 C1, right? Then you will get a pole as minus 1 upon R2 C2. So now,
Ma'am, here small doubt, ma'am. Why we are equating these to 0, ma'am? Whenever we are finding, why we are equating to 0, especially.
okay, so the idea when we say 0, 0 is the frequency for which your gain goes to 0. Okay?
Oh, okay. That is the reason, right?
And similarly, pole, when we say pole transfer function goes to infinity. The frequency for which your gain goes to infinity, that frequency is known as pole frequency. The frequency for which your transfer function or gain goes to 0, that frequency is known as zero.
Okay. For pole also we are equating to 0 only, no? What makes the difference, ma'am?
No. For 0, you are equating numerator to 0. For pole, you are equating denominator to 0. That is it.
Okay, 1 by 0 is nothing but infinity, like that.
Yes.
Okay, thank you.
Because pole is when your transfer function attains maxima or infinity. So when you get an infinity, so anything by 0 will give you infinity, right? And similarly, anything multiplied by a 0 will give you a 0. So with that concept, we find the zeros and poles. Clear?
Yes, ma'am. Clear, ma'am.
Frequency unit for these poles and zeros. The unit.
Unit, it unitless, ma'am.
Huh?
It is unitless, no?
No. So these are actually radian per second. These are the radian.
Omega.
So these are the values of omegas.
Omegas.
Omega Z and omega P. Now, if you want to find the frequency in terms of hertz, how did you write? Omega is 2 pi into x, right?
Yeah.
So you have to keep this in mind that whenever you are solving your transfer function, you'll either solve it in terms of g omega or you'll solve it as x in forms of x, right? So the result that you get is for omega. So when it is asked, okay, if you are asked in terms of hertz, kilohertz, megahertz, you have to make sure that you solve with this 2 pi. Like you have to take care of this factor 2 pi over there. Otherwise, you will always get like the basic solution that you will get is in radians per second. If you want it in hertz, then you have to solve for, like you have to consider the factor of 2 pi over there. Because many of the times people do these mistakes and it is a very silly mistake, but yeah, it's a mistake. Like you have to be very clear, okay, what are the results you are getting, whether they are in radians or whether it is in hertz. You have to be very clear about that. Am I clear?
Ma'am, clear, ma'am.
Okay. Okay. So yeah, we have found out like 0 is 1 upon R1 C1 and pole is 1 upon R2 C2. We'll simply substitute the values of R1 C1, R2 C2 and get the values of poles and zeros. The first question was on pole and second question was on zero. So if we substitute the values, we can easily find like for pole, the value is minus 92.68 and for zero, it is 32.96. Okay. So R1, C1, R2, C2 are already given. You have to just use the value. Okay. So let's move on to the next problem. So in this problem, again, in this particular circuit, assume that the K is 86 millisiemens per volt, lambda is 0.1 volt inverse. This is for the MOSFET. And op-amp gain, the gain of this op-amp is 554. RL is 43 ohms and the input voltage is 1.2 volts. Okay. Revision that, what is the output impedance looking into the source of the MOSFET device? So that give your answers in milliamps. And you have to make sure that you do not disconnect the op-amp like while computing the output impedance. With this, we have to use this feedback connection. It is already mentioned. Here, the current that is flowing through this. So first of all, when I say that this is an op-amp and it is giving you like a gain, good amount of gain, we'll consider the virtual short constant and we'll say, okay, both the nodes will have same voltage. So here again, you'll have 1.2 volts. That means here also you will have 1.2 volts, right? We know that there is no input current, correct? So whatever current that is flowing through your transistor, the same current will flow through your resistor, right? Because your transistor and resistor are now in series. So how do you find your ID? You can find your ID as, let's give it some name, V out. This is node V out by RL. We'll give you ID. So it is 1.2 upon
27.28 milliamperes, ma'am.
yes, 27.9 milliamperes. So this is the current that is flowing through your op-amp, your transistor, MOSFET. Now, okay, so your transistor has this much amount flowing through it. Next, the question is, okay, what is the resistance looking from your this source side, right? We have to find the Z out from source side. So how do we find Z out from source side?
That is output.
Yes, that is out. Drain, gate, source. So at this node, what's the output? What is the node impedance that you see from source side? So for now, let's do one thing. So we know that we need GM and GD, right? So let's calculate the GM and GD first and then see how we'll proceed, okay? So let's find out GM for the given transistor. How do you find GM? It is 2 root under K into ID, right? So it is 2 into root over 86 millisiemens per volt into ID is how much? 27.9 milliamperes. So it will give you 97.96 millisiemens. And for GD, it is lambda into ID, so which is 0.1 into 27.9, that is 2.8 millisiemens. So you've got your GD and GM. And you can write R naught also, like 1 plus 1 upon lambda ID or 1 upon GD, which will give you like 358.4. Now the question is, okay, so if you observe at this particular point, like what is the gain that you will get? So here, when you are considering your configuration for output impedance, how do you calculate output impedance? Practically speaking, how do you observe output impedance? So you apply a small voltage V, and you have a small, like Vs, you have a small current Is. So Z out is found out as Vs upon Ix. Now in this particular case, it is made sure that all other sources are grounded. So that means this input will be grounded. Okay. While calculating your output impedance, you will only have one single source at a time. So you will use that source at the output node and you will put your input to ground. Now, when we say op-amp output, we can write op-amp output as V plus minus V minus into A. Gain times of differential voltage will give you the output in an op-amp. Okay. So here, V out is equal to A times of what is V plus, we have put it to ground, so 0, minus V minus. What is V minus? Actually, if you observe very carefully, it is Vx only, right? What is V minus? So it is connected to this node, right? Output node. So it is Vx only. So V out is equal to minus of AVx. So at this node, the gate voltage is minus of A into Vx. Correct? So we know for a transistor, like first thing, Vg is equal to minus of A into Vx. From small signal analysis, we already know that ID equal to GM plus GD correct? GM plus GD. Now here your VD is AC grounded. You only have VS. So you can write your small ID as your small ID as VN, VG that is minus A times of VS minus VS which is VS plus GD into VD is 0 minus VS is VS. Correct? Any doubts till this point? Yes, any doubts? No doubts, right? Okay. So ID is minus Gn 1 plus A into Gx plus Gd minus Gd Vx. So this is your ID. This is ID. So one thing that we can observe is, it was mentioned that we can discard RL, right? In the question, it was already mentioned that you can discard RL. So considering there is no current flowing through the RL, and we already know there is no current entering into your op-amp. So if you observe very carefully, your ID is equal to IS, correct? Like ID is equal to IS. It's just that your signs are reversed. So your ID is minus of IS. So your IS is minus ID. So your IS is GM1 plus A minus GD, plus GD into G8. Now Z out, what did I mention Z out as? Vx upon Ix. So from here you can find your Z out, right? From this expression. Vx upon Ix is how much? 1 upon Gn1 plus A plus Gd. Correct? Now here we can simply substitute the value and solve it. So this is 1 upon, and you can write it in terms of R naught also. So it will be like Gn R naught 1 plus A plus 1. So you can write it either way. It is up to you. So it is like 1 upon 97.96 milli into 1 plus 554, right? 554 plus how much is this? 2.8. So Z out, that is Vx upon Is, is 184. No, 18.4. Yes, 18.4 million. So this is the value that we get. It is 18.4 million. So one more interesting thing to observe, as I mentioned, that source impedance is very small in our exam, and you can clearly see that the source impedance is in milliohms, which is very small. So the lowest is source impedance. So you're getting the correct result. So you can like do some sanity check also by this. So by checking, okay, if the values, whether you are getting the correct values or not, the units are correct or not, you can do some sanity check by that. So is this clear? Any doubt in this problem? Now, similarly, there is another problem. Now here what has changed, so in place of PMOS, in place of NMOS, there is a PMOS. Here input was given to non-inverting terminal. Here the input has been given to your inverting terminal. And you have to again find the output impedance. Everything remains the same, only the terminals have been changed, and here the PMOS has been introduced. So can you solve this problem the similar way as you did for the previous problem? I'll write down the final expression that you should get. So after solving, the expression that you will get is 1 upon 1 plus Gn R naught into A, and the value will be 18.42 million. So you should get this expression after solving. So only PMOS has been changed by NMOS, and your positive and negative terminals have been interchanged. You will solve this problem. Just in case if you face any difficulty, you can let me know in the next session. Okay?
Okay, ma'am.
Just PMOS has been changed, and the terminals are everything. Okay. Let's move on to the next problem. So in this problem, this particular circuit that you are observing is a sine wave oscillator. It will give you oscillations per sine wave. So here it is mentioned that total capacitance is 24 picofarad. C total is 24 picofarad. And since there are two capacitors, both have been named QC, that means ideally it is considered that both the capacitors are equal. So each capacitor is of 12 picofarad. So now it is asked that what should be the value of R such that the circuit oscillates at 1 megahertz. So the frequency of oscillation is 1 megahertz. And what is the value of R for that? So how do you get the oscillation frequency? It is 1 upon 2 pi R into C. So you'll get the value of R by 1 upon 2 pi into 1 megahertz into 12 picofarad. So when you solve this, the value of R will be 13.26 kilo. Okay? Here, the frequency is given up by 1 upon 2 pi RC. For basic circuits, for basic RC network, the frequency is 1 upon 2 pi RC. So that's how we got that. Coming to this next problem. So in this problem,
Please explain a little bit more about previous problem, ma'am.
in this problem, you have to find, so it is like oscillation frequency is required for this particular circuit. So when this type of circuit is there, so what you will do, to understand it like very briefly, you find out okay what is the very basic circuit in this. What is the basic circuit? So it is like R, there is a C, and there this
With my understanding, ma'am, second block is acting as an integrator, and
also an indicator.
yes, third op amp is acting as a inverting amplifier.
Yes. So here, what is the basic building block from where you will get the frequency component is where you will see the C's, right? This cannot give you the frequency components. Ideally, we consider like op-amp internal capacitors. We don't consider. So since there is no external capacitor, you don't have to care about okay this particular term as it will not introduce any capacitive or frequency dependent term. So now looking at these two, so these two are similar structures, right? So there is a resistor in feedback with a capacitor. Here also a resistor in feedback with a capacitor. So the basic is this circuit. A resistor and capacitor circuit. Here it is Vn and here it is Vout. Now let's write like KCL at this node. So 0 minus Vn by R plus 0 minus Vout by 1 upon 12 plus 0. So Vout is 1 upon Cs into minus Vn by R. So Vout by Vn is minus 1 upon RCS. Right? So here, yes. So the transfer function is minus 1 upon RCS. So for this transfer function, if you observe very carefully, so for your oscillating frequency, what we see that the gain should be 1, the overall gain of your system should be 1, and the phase should be 360 degrees for oscillation. So, but here, so this is your Vout by Vn. So if I put my S as 1 upon RC. So what I'll get, if my S is 1 upon RC, then my V out by Vn will be 1, right? Minus 1 or 1. And now if let's say I feed back again, so the feedback loop has a gain of 1. There is no component in the feedback. And my this gain
Acting as a voltage buffer number.
acting as a voltage buffer. So here, that's what I said. What I said for oscillation, total gain of your circuit, total gain should be 1 and phase should be 0 or 360 degrees. So this is when you get a sustained oscillation. So here it was a basic circuit with R and C. So we simply, for this circuit, we know that we will get 1 by RC as our resonant frequency. Otherwise, if there is some other circuit, what is the best way to solve? You solve the transfer function for that circuit, that is V out by Vn. Now what you do, you check the phase and you check its magnitude. And what is the frequency for which your total gain becomes 1 and your phase becomes either 0 degrees or 360 degrees? That value of omega will be a resonant frequency. Here the circuit was simple, like simple R and C, only one R and one C. So we know for this type of circuit, the resonance frequency is given by 1 upon RC. And if I'm saying frequency, then S in hertz, so I want 1 upon 2 pi RC. So that's why I wrote it down directly. Otherwise, if there is some complex circuit or some circuit, like for this particular circuit, if you don't know like what you will get, the best way to solve is find the transfer function. It's yourself. Now the next task is you have to see that your total gain should be 1 and total phase should be 0. Okay. And
Thank you, ma'am.
okay. So you will be like there is a feed forward and a feedback path. So let's say I'll break my circuit from here. So here the feed forward path will be like this, right? So this point will be my V in and this is my V out. So V out by V in V out by V in is feed forward and there is another path which is like feedback path, right? Which is like from V out to this connection. So for that, how would you write? You will write it as V in by V out. This is feedback. And when I say your gain should be 1 and total phase should be 360, I am talking about considering both. So that means V out by V in into V in by V out should be 1. And that frequency omega will be your, for which you will get this gain as 1, that omega is your oscillation frequency. And similarly, combined phase of feed forward and feedback path. You'll add both the phases and you should get 0 or 360 degrees. So whichever frequency will give you 0 degrees or 360 degrees phase or any multiples of 360, then that particular frequency will be your oscillating frequency. Clear?
How to say a phase shift exactly?
Phase shift, how to, sorry, I didn't get your point. Like, what
How
is your
to
doubt?
see, how to get the phase shift in circuit?
Phase shift. You have to solve phase shift for a circuit. Okay. So let's say if
We
you
can
have a transfer function saying 1 upon a plus sb. Okay. Very basic transfer function. Now, how to write the phase of this function? So it's there in basic like complex numbers and like how you write the phase of a complex number. So that is the same thing you'll use it here. So it is like first of all in denominator, so negative, tan inverse, it is b by a. So the phase of this transfer function is minus tan inverse b by a. Now h of s, let's say it is minus 1. What is so if let's say my h of s is minus 1, what is the phase of the system?
180.
Yes, h2 of s is 180 degrees. Now if it was like h3 of s, let's say, we have h3 of s is 1. Then what is the phase?
0.
0 degrees. Now let's say h4 of s is same, a plus sb, but it's in numerator. So how do you write the phase h4 of s?
Inverse b by a.
Tan inverse b by a. So that's how you write the phase for your system.
By looking at the circuit, it is an inverting op amp. The
Sorry.
phase shift is 180. The above circuit.
Huh?
In circuit, it is an inverting op amp. So the phase shift is 180. For each stage, it is 180.
Okay, so you're saying, okay, so this is a inverting op amp, so the phase shift is 180. So for oscillation, your inverting phase should also come as 180, like inverting terminal. So this is also connected to your inverting input, right? See,
Yes, ma'am.
180-degree phase you will get when you are traveling from input to output, correct? Because it is connected in inverting phase. So 180 degrees. Now, when you are going for feedback, how you are connecting your feedback, your Vout is again being connected to inverting, right?
Yes, ma'am.
Vout is not connected to plus terminal, rather it is connected to your negative terminal, right? So it will also introduce a 180 degree phase shift. So that's plus 180. So the total it becomes 360 degrees. Right? So the total phase, so this is something you have to keep in mind. Like for oscillation, your total like gain should be 1 and phase should be either 0 or 360 degrees. Okay? Clear, right? Any doubts in this? Like this is also known as Barkhausen criteria. Criteria for oscillation. Like this is very famous criteria for oscillation. Whenever you see oscillators, these criteria for any circuit needs to satisfy these two conditions for getting sustained oscillation. Okay. Now let's move on to the next problem. And I guess okay. So in this particular problem, there is this resistor RA of 18 kilo ohms and RB of 225 kilo ohms each. The question is you have to find like the CMRR for the given circuit. So now for this particular circuit, what do you understand by CMRR? What is CMRR? Yes, what is CMRR?
Common mode rejection ratio.
How do you write CMRR?
1 plus GM into RL, right? Sorry, there would be some formula. I forgot it.
So
Differential can be common mode.
AD by ACM. So AD like differential mode gain when both the inputs are different. Common mode gain when both the inputs are same. So for the given circuit, let's solve this for differential input, that is Vin plus and Vin minus, what we will get. Okay. So for Vn plus, if there you have a Vn plus, here again you will get a Vn plus. If here you have Vn minus, here again you will get a Vn minus. Correct? So now at this particular node, that is A and B, let's write KCL. Okay? KCL at A, it will be Vn plus minus Vn minus by RA, this Vn plus minus V out plus by RB equal to 0. Only two currents, right? Similarly, KCL at B, you will get Vn minus Vn plus by RA plus Vn minus V out minus by RB equal to 0. Now these two are equal, so we can equate them. So it is Vn plus minus Vn minus by RA plus Vn plus minus Vn minus V out plus by RB is equal to Vn minus Vn plus by RA plus Vn minus V out minus by RB. So Vn plus let us like Vn plus Vn plus 2 by RA, this one has come this side, and plus 1 by RB, and similarly if I bring like Vn minus to this side and this one also again to this side, so I will get minus Vn minus 2 by RA plus 1 by RB is equal to, I'm sending your V out plus to this side. So it will be V out plus minus V out minus upon RB. So that is Vn plus minus Vn minus 2 by RA plus 1 by RB is equal to V out plus minus V out minus by RB. So how do you write AD? AD you can write it as V out plus minus V out minus by Vn plus minus Vn minus. So from above, you can write your AD as RB 2 upon RA plus 1 by RB is your AD. Correct? Any doubts in this? How did we come to this point? Is it clear to everyone? AD formula?
Yes, ma'am. Yes.
Okay. For this, now we are solving for ACM. So ACM, both of the inputs need to be same. So if both the inputs are same, let's say it is Vn naught, here it is again Vn naught. So then means here also you will have Vn naught and here also you will have Vn naught. So if both the voltages are Vn naught for both the resistors, is there any current that is going to flow through this resistor? No current will flow through it, right? So we can write it as a the open circuit thing. So this is equivalent to, if I draw it like this. V out, V in, plus minus, V out, V in, minus, RB, RB. So if you observe very carefully, here what has happened, since these two resistors, across RA, both the potentials are equal, so no current will flow through RA. So it is ideally behaving as an open circuit. If there is an open circuit, there won't be any current which is flowing through it, right? So because of that, you observe very carefully, the and actually they start behaving as a buffer. So here V out by Vn is 1. Is it clear to everyone? Now what is your CMRR? It is AD by ACM, correct? You already know your AD, that is RB 2 upon RA plus 1 upon RB by 1. So CMRR, you can simply substitute the values of your resistors, that is 225K, 2 upon 18K plus 19, and 1 upon 225K. So the CMRR that you actually get, it is 28.29 dB. Most of the time CMRR is reported in dB. Ideally CMRR is reported in dB. In question it was also asked to report in dB. So the CMRR that you get for this particular circuit is 28.29 dB. Is it clear to everyone?
Ma'am, here the op-amps are becoming independent and they both are identical. So suppose if the resistor value is different, like here both RB are present, then in that case, like what we will do, like consider.
So if let's say instead of RB, it was RB1 and RB3.
Yeah.
The circuit will act as a buffer circuit. So that is V out equal to Vn. Because there is no current that can flow through this resistor, right?
So we can consider any one of them and just okay.
Over here, or even a circuit, in any case, it will act as a buffer.
Okay.
V out is equal to Vn.
Can you please tell us how it became open circuit, ma'am, in the two op-amps?
Mentioned already, right? The potential across both the resistors, like across both the terminals of a resistor, are equal. So
Okay.
if terminal resistors are terminal potentials of a resistor is equal, will it lead to any current flow in that resistor?
Mhm.
Because current flows, there is a potential difference, right?
Yeah, it has a potential difference. Yeah.
Yes. But here there is no potential difference. So if there is no potential difference, means no current. Which
Okay.
other we find that there is no current? The condition when there is an open circuit, right?
Okay.
Circuit also does not does not allow any current flow. So it is like equivalent, right? Both the situations. So that's why we drew an equivalent circuit with open circuit and then we analyze. Okay?
Yeah.
Okay. So let's move on to the last problem for today. So in this problem we have R1 as 16K, R2 as 29K, and R3 as 42 kilo resistance respectively. Now what is the input impedance of this circuit that is given? So what is the input impedance is something that we need to find out. So if you observe the circuit very carefully, I'll draw it again for you to make that look very easy. You have your VR. Here there is VM, R1, R2, and R3 and R2. So if we eliminate, if there was no R1 present, so let's say these two connections are not present, so then your op-amp appears as an non-inverting amplifier, right? So if you want to write your op-amp without R1, your V out by Vn is 1 plus R2 upon R3, correct? Now there is another resistor R1 present over here, and you have to say, okay, what is your Zin? So let's say if you have connected a Vn, it provides the current In. So what is Zin? That is Vn by In. So that is what you need to know. So if here you have Vn, here you have V out, you know that no current can flow through here, so definitely a current can flow from here. So the current through your resistor R1, IR1 is actually your current IN, which is Vn minus V out by R1, right? So Vn minus V out by R1. So now from here, let's say we are getting our V out value. So Vn 1 minus 1 plus R2 by R3 upon R1 is In. So Vn by In will be how much? R1 upon 1 minus 1 plus R2 by R3. So this 1 minus 1 cancel. Is R1 R3 by R2, which is your Zn. And because it is the whole time, so N minus. So the value of Zn is minus R1 R3 by R2, which is equal to 20 minus 23.70 kilo. So this is the resistance within that you get. Okay, and put is it clear? Is it clear to everyone? Is this problem clear? So with this problem, we are done with the problem set for today. If there are no doubts, and break over here and
Oh, ma'am, actually, there are like few doubts in the assignment, which are there. So solution is already present in NPTEL, but still, I have some doubts. Like, it is like directly written some formula, but when I am solving through like equations, so I am having some doubt. So can we discuss?
so sometimes what happens, the formulas which are given, and when you derive, so when you derive, you are deriving it, let's say, for a complete length. But after that, there are few assumptions which are made, and based on this assumption, it is actually the formula is further reduced to a smaller thing. So you might be saying that you are getting a very huge formula, but the formula which is present in the solution is very smaller one. The reason behind it, the assumptions which are made. And for that, you can, I guess you can follow the lectures because the formulas which are used in your assignment, those formulas are most of the times already discussed in the lectures. So you can see how that formula has been reduced, like what were the assumptions that are made, when you can make those assumptions. And so that you can follow that, like where you are getting that reduced formula from. So, yeah.
Okay, sure.
In lectures, formulas are derived, right? So the
Mhm.
formulas are derived that way. You can see, okay, what are the assumptions that are being made, where you can,
Mhm.
so you can go through that. Yeah. Most of the
Madam,
majority of the times are there in lectures. Yes,
madam, when you're using the MOSFET in the diode configuration, that
yes,
is by shorting the gate and drain,
yes.
in that case, you have to consider minus GM
In that case, you have to consider minus GM.
for calculation of, transconductance. You have to consider minus GM, ma'am.
No, no. See, transconductance, you will get one value.
Okay.
Minus plus, it is
The
ideally
polarity.
polarity. When do you need that? When you are calculating, let's say, gain, and you know that, okay, for CS amplifier, you should get 180 degrees gain, like 180 degrees phase. Now that 180 degrees phase, how do you represent that? You use a negative sign. But
Okay.
solving, because see, when there are formulas, like if you are calculating GM or current, these formulas ideally will be positive only, right? Majority of.
Yeah.
So yeah, formulas you will never get positive or negative. Then positive negative majorly is used to show that phase shift. So generally when we say, okay, gain का formula क्या होगा? What is the gain formula? We generally say GM into Z out. But if it is CS amplifier, it should actually be minus GM into Z out. That minus is very important for a CS amplifier. Correct?
Yeah, ma'am, in some of the numericals, they have considered minus GM and saying that it is because it is at a negative, this one, it is they have considered minus. Apart from the minus, this one GM1, I mean the GM of the transistor, V input transistor, the transistor conductance they are calculated, they are considered, ma'am, this one minus GM. For the GM2, rather, the output transistor, output, what do you call it, the output MOSFET in the diode configuration.
Diode configuration.
At the output side, ma'am, on the PMOS side, say about PMOS side, we are
Oh,
taking this one, they have to consider minus GM. I don't follow that. That's why I'm asking you, ma'am.
so your PMOS, you were saying. Okay, let's say you have a PMOS.
Yeah, that's right. That's right.
You have a PMOS and you are saying like you want to find write GM, correct?
Yeah, yeah.
So how do you write it? Like GM into VSG plus GD into VUC, correct? This is
Yeah,
the
that's right. That's
basic
right.
formula.
Yeah,
And we are saying that it is in diode concentration. So GD
yeah,
is
that's right. That's right.
MSGD. So ID will be GM. Now let's say it is VDD, right? So when we are doing AC analysis, that means it is AC grounded.
Grounded. Yeah, yeah, yeah.
So V0 minus VD plus GD into 0 minus again VG, because VG is equal to VD.
Yeah,
ID equal to GM plus GD into VG minus, correct?
yeah, madam.
So
Yes, madam.
yeah, so you are getting a negative over here, right? So that negative is because how your voltages are there. Like it is already coming from here, no? So it's not like, not that your GM will give a negative value.
Okay,
Because,
but in some numericals, madam, they have solved. They have indicated numerical value, especially in the output side.
no, see, because when you write GM, what is your GM? It is mu and CS W by L, VGS minus VGS. For your transistor to turn on, your VGS should always be greater than VGS, correct?
That's right. Yeah, yeah, that's
So
right.
always correct, your GM will always be a positive value, correct?
Hmm. Yes.
So yeah.
I don't know. Some of them, I don't know. Anyway, I will point out. I will write it to them. I mean,
Yeah, maybe you can analyze it further, like what they are trying to say. Maybe you might have misunderstood something.
any which way, ma'am, it is positive. It should be positive.
It will be positive. It should. See, DM will always be positive. Resistor value is always positive. Now, like, what does the negative resistance mean? So generally, a resistor is a positive thing.
Yes, yes.
It is something very complicated and very, but we
Yeah,
don't do that. Ideally, when we get okay negative value of resistance, so we remove current direction and it is voltage direction.
that's right. That is right, ma'am. Yeah.
It is positive. So DM is also positive.
Okay.
Might turn out that while solving, like here also, if I say, okay, my ID by VG, I'm getting a negative of DM plus VG, right? So I'm getting a negative, and ID by VG is again a transconductance, correct?
Yeah.
So this is a combination of transconductance, and I'm getting a negative transconductance. That doesn't mean it is negative. It's just that because of the interaction between those two, we get it. But VD will be a positive value, right? Always.
Yeah.
Maybe you can go through it once again and like what they are trying to explain. There might be some confusion. Okay. Or if it is something that you feel like something is really wrong, you can write in the forum and respond.
Well, one more thing, this GM, they have indicated millisiemens per volt. It should be millisiemens per volt, no? The unit.
For GM,
Huh?
for GM, you are saying the unit is millisiemens per volt.
Yeah, I mean, that is what they are indicating. Millisiemens per volt or millisiemens?
No, GM is always millisiemens.
Millisiemens, okay. Okay.
Siemens is for, like, ohms is for resistor, right?
Okay.
Maho or Siemens is for.
Okay. Yeah. GM, sorry, it's not GM, ma'am. I'm talking about, talking about the this one, K factor. K factor.
K factor will be.
Sorry, ma'am. It is K factor. Millisiemens per volt, no, it should be.
Yes, per volt.
Because as you rightly said, some of the answers, I mean, numericals, you have to see the units because that will should match. Then it will give a right. That will give a right discount.
Yes, units are very important. Always
And
consider.
lastly, ma'am, one more thing. You have in the MOSFET, you have three basic. This one is GM, then is RDS, which is parallel to each other, and then RO. Correct, ma'am? In case of lambda comes in the picture.
I don't follow you. What you are trying to say? What are
Ma'am, in the MOS circuit, the internal MOS circuit, GM and GM is parallel to RDS, correct?
so you are talking about the small signal model?
Yeah, small signal model. Yeah.
Small signal, you will have GM into VGS as a current source. Then to that, there will be another resistor, let's say R0, which is from like drain side that you see. And then if you are connecting another like a drain resistor, then it will come it's drain. Otherwise, if it is a source resistor, it will come to source. So you have to see where it is coming. But internally, what are present is one GM into VGS, and secondly, the small R0, which you get from 1 by VD.
Okay. RDS is not present, madam. RDS, the resistor drain and source.
RDS is something. So you can write like it depends. See, your small R0 can also be your RDS. GD we write. We can write it as
Yeah.
GDS. It is a
GD. Okay. Okay.
GD is also equivalent to GDS. R0, the small R0 is also equal to small RDS. So it is
Okay.
the difference between your drain and source terminal internally. That comes because of lambda.
Okay, because of lambda. Now, ma'am, in the triode region, when you consider it will basically act like a resistor, correct? Because voltage and currents are increasing or decreasing proportionately, rather increasing proportionately. This is the point of DC break-even point, correct, ma'am?
Yes.
Now, after that point of threshold is gone and we go into saturation region, the curve has to be flat to flat and has to be parallel to the x-axis, that is parallel to VDS values.
Yes.
Correct? But there are some deviation because of the channel length modulation. That's why you find some inclination in that. Correct, ma'am?
Yes.
And that is what you call the slope, that is delta ID by delta VDS is, we call it that slope. Correct?
Yes.
Okay. And that resistance, I mean that the values which varies in the triode region, we are not considering those values because those values are primary. We are considering the MOSFET in the saturation mode, in the amplification mode. Correct, ma'am?
Yeah, when we are considering like saturation region, we don't talk about triode region or any other region. It will only focus on saturation region, their conditions and everything.
Okay.
We never talk about triode region.
Thank you, ma'am. Thank you.
Okay. Any other doubts? So if there are no doubts, maybe we can break over here and meet at the next place. So that's all for today.
Yeah.
Thank you, everyone.
Yeah. Thanks for your time and guidance, ma'am. Thank you.
Thank you. Thank you for joining the session and have a wonderful evening ahead. And let's meet again next week. See you all. Bye. Good night.
Bye. Good night.
Bye. Thank you. Bye.
Sorry.
Yeah, bye bye. Thank you.
Bye. Yeah. Bye.
Bye. Bye.
Thank you. Bye, everyone.